We yesterday said that when we fit a viable distribution to failure data, we end up with a density function like this. This is the viable distribution itself. And this viable distribution will have a certain value of beta, which is a shape parameter, and it also has another number which is eta, which is its scale parameter, which gives an indication of its scale. Now, what we now want to find, this is now a reality in terms of the failures that we've experienced for the specific component. We need to find out whether we can cut the life of the component short by replacing it at an earlier life, and so obtain benefit for the organization. This distribution is part of the information that we have. This also determines the risk profile for the failures of this specific component. So that is the one part of our information. The other part of our information is cost information, which is based on the following formulas. We encountered these two formulas yesterday. Firstly, there's the cost of failure CF, and secondly the cost of prevention CP, and in both cases they consist of the cost of spare parts, the cost of labor, and the cost value of lost production, firstly in the case of failure and secondly in the case of prevention. So what do we have? We have some component of which we are investigating the failure. We have failure data of that component. Based on that failure data, we can construct an distribution function. And we have some costs for prevention and costs for failure. And we now want to combine these two quantities, the actual failure behavior of the component, which we have now pictured in terms of an distribution, and we have some cost figures, and we want to take these two pieces of information and we want to put it together and eventually end up with how often should we replace this component preventively so that we end up with the lowest possible cost for the organization. And that cost for the organization includes labor cost, includes spares cost, and includes also the loss of production cost. So what do we get if we combine these two pieces of information? The failure data, failure information that we've compiled into a density function from which we derive the force of mortality function, which shows the risk of failure, and then also the cost figures that we have. We eventually end up with a figure TP, which is the time to preventive replacement. And when we then have a new component, then hopefully the component will run until it reaches that life TP. We will then replace it preventively, and that replacement process will take a certain period of time, which we have here as capital TP. But we also know that sometimes we won't be successful. When we have a new component, it will run, but it will not reach the life TP, but before the life TP is reached, it will fail at some life which we called TF. In this figure here it is shown as TC as being corrective maintenance. We've called it TF. Then it will fail, and then it will take us some time, either TC or TF, that we need to repair that component again to the new condition. So what this picture shows us is that we have two cycles. Sometimes we will have a successful cycle, and this successful cycle will entail that we eventually end up with a new component that is replaced preventively after the preventive age has been reached. And sometimes we will not have that success, and the component will fail before it reaches TP, and we will thus have a failure cycle or a corrective cycle like it is depicted here. Yesterday, when we talked about deriving the cumulative distribution function from the density function, we had this picture on the slide. Now, what we said is that the cumulative distribution function is really the accumulation of the area under the density function. So thus, if one takes an accumulation up to a certain point, in other words, calculate the area under the curve at this point, we get the number of the percentage of components that will fail at or before that age. So thus it now gives us here the number ft, which is the cumulative distribution function, or the cumulative percentage of failures from 0 up to that point. Of course, also that means that 1 minus that figure, in other words this quantity here, will give you the percentage of units that will survive up to this point. If we now go back to our density function, and if we assume that we know at what life we are going to replace the component preventively, and we call that TP. Of course we do not know that, we want to establish that life. That's the purpose of this whole exercise. Then we would, from the previous discussion, we would say that this area here represents the percentage of components that will fail before or at that life TP, and thus they will be components that will be replaced under failure circumstances. On the other hand, the area on the other side of TP will represent the components that will survive up to TP, RTP, and thus they will be the percentage of components that we will be replacing preventively. Also, because the area under this whole curve is 1, representing a failure, total failure possibility of 1 or 100%, we can then say this quantity here, which we represented by FTP, we could also write as 1 minus RTP, so that that area plus that area will then add up to a total of 100% probability of failure. So what we now have is we have this area here, or the figure 1 minus RTP then represents the percentage of components that will fail before they reach TP and which will be replaced under failure circumstances. Whereas this area here, RTP, represents those percentage of components that will reach TP and that will be replaced preventively. So in summary, this is now what we have. We have this table summarizing everything. We have two types of cycles, a preventive cycle and a failure cycle, which is the cycles that we have down here. The cost of the preventive cycle is CP, the cost of the failure cycle is CF, and that we've defined up there. The prevalence of each of the cycles, in other words the percentage of cases in which those cycles will occur, is RTP for the preventive cycle, which we showed here, and 1 minus RTP for the failure cycle. And the cycle lengths are TP plus TP for the preventive cycle, and TF plus TF for the failure cycle. So now we can calculate the cost of a typical cycle, or let's call it the average cost of a cycle, because in some cases we will have a preventive cycle, in other cases we will have a corrective cycle, dependent on this split here. In the case of a preventive cycle, the cost will be CP and the prevalence will be RTP, or the percentage of cases in which that cost will prevail. And in the case of a failure cycle, the cost will be CF and the prevalence will be 1 minus RTP, or the percentage in cases in which that cost will prevail. And the total will give us the total cost of an average cycle, or then a typical cycle. Similarly, the length of a typical cycle is given by the length of a preventive cycle plus the length of a failure cycle. And again, the length of a preventive cycle is the actual length, TP plus TP, multiplied by the prevalence of a preventive cycle, plus the length of a failure cycle, TF plus TF, multiplied by the prevalence of a failure cycle. The one problem that we sit with here is that the length of a failure cycle, TF, is an unknown or is variable. The length of a failure cycle can be anywhere between 0 and TP. In other words, the component can maybe fail here, or it can fail here, or it can fail here, each time with a different probability of it failing. And because of that, what we need in this formula here is we need to replace that quantity TF with the average failure life of a component, given that we replace the component preventively when it reaches TP. To illustrate how I can calculate the expected failure life of a component, given that if it reaches the life of TP it will be replaced preventively, we can make use of an example. If I have a class of students and I want to know what the average marks of the students are, I can take the mark of each student and add it together and then divide it by the number of students. But if I want to make it simpler, I can divide my marks up into intervals as we have it here, intervals of 0 to 10%, 11 to 20%, and so forth up to 91 to 100%. And then I can just count the number of students that there is in each of the intervals. What I can then do is I can say, well, my estimate in the interval 31 to 40% is 35%, the midpoint. So 35% times 2 students gives me an estimated 70 marks in that interval. Likewise, 45 times 3 gives me 135 marks in that interval. So what I then do is I add up all my marks, my estimated total marks, and I also add up my number of students, and I then divide the number of students into the total estimated marks, and that gives me an estimated average mark for per student of 61%. Now the smaller those intervals become, the nearer my estimate will be to the real average marks of the student, to such a point that when my interval width becomes 1, then I will have the actual mark that I would have had if I added up the actual marks of the students and divided it by the number of students. Now if we apply this principle to our failure situation to calculate what the expected failure life of a component is, given that if it reaches TP it will be replaced preventively, we can take a part of the density function and blow it up a little bit, and we can then take an interval. In other words, the same principle there. We can take an interval of width dt. In that case the interval width was 10, and we can then calculate the weight of this interval, whereas we used the number of students there as a weight. We can calculate the weight by taking the area here. So we say, well, the average height of the interval here was ft, and the width was dt, so we have ft dt, and we multiply that with the value which is t, so we have t ft dt, and we sum that over the whole area from 0 up to TP. We sum that, which is an integration process, and we then divide it by the total weight. In this case we divided that total by the total number of students, which was 25. The total weight here is then the total area there, 1 minus RTP, and that gives us the expected life of a component given that it will be replaced preventively if it gets to TP. We can now put everything together. We originally calculated the total cycle cost, or the average or typical cycle cost. We also calculated the typical or average cycle length. We can now calculate the cost per time unit by dividing LE into CT, which will give us this. But we sit with the problematics that TF is not a single figure, and that we can solve by replacing TF by this quantity here, which we just calculated, which is the expected life given that replacement will take place at TP preventively. So we replace that, and we thus get that integral term in this formula here, and this will now give us our cost per unit time, which we can then calculate for different values of TP, and we can, by experimentation, we can then produce a graph of the cost per unit time, which we can then use to find the minimum cost of maintenance, in other words the value of TP which you should practice if you want to have the minimum maintenance cost. We can now see the result of where we've been heading. We have this cost per unit of time formula, and if we draw that, we will get a graph like this, which experiments with different values of TP and then produces a cost per unit time for various values of TP. And the idea is then that we want to find this minimum value of the cost, the value of TP, which we call TP star here, which gives us the minimum cost value CTP star. So that is our objective. Now, something that is very important in illustrating the process and making sure that one understands is that we go and we then break up this formula into two parts. We break it up into the preventive part, which is this part here, CP RTP divided by this whole thing here, plus the failure part, which is CF times 1 minus RTP divided by that whole term again. So we just break up the total formula into two parts, and this part we can then draw separately, and we can draw this one separately, and that gives us this result. So we have the cost of prevention here, and we have the cost of failure, and then we have the total cost, which is this graph on the left hand side here. So we can then see what part of this total graph is made up by the cost of prevention and what part is made up by the cost of failure. And in the remainder of this session, of this demonstration, we will now go and we will illustrate this with actual figures.